This is probably the last section of this alcohols and the cell chapter, chapter 16. We're talking about a little bit more about the spectroscopic analysis of alcohol in the cell. First thing about alcohols is infrared, and the infrared most signature, the feature of alcohols is the OH stretching peak. Because because infrared absorption peaks are directly associated with the dipole moment change, the happen during the vibration. And for stretching vibration, we directly look at the dipole moment of the functional groups. Because OH group is very, very polar. The dipole moment, the difference is very large. O is about 3.5, H is about 2. So this is a very large dipole moment change. So that's why OH stretching vibration is very good at absorbing infrared photons. So you have OH group, it's very difficult for you to miss it. And also because OH group can involve in hydrogen bond. So OH infrared peak is always strong and broad, usually. Okay, and it's between somewhere 32 to 3500. You kind of very difficult to miss it. And you also can have CO stretching vibration. And if it's a regular alcohol, the CO stretching vibration usually either at or slightly below 1100 reciprocal centimeter. This is the CO stretching here. Okay, OH stretching, CO stretching, slightly below 1100 in the reciprocal centimeter. And in this particular molecule, cyclohexanol, you also have a lot of sp3 CH, okay, slightly below 3000 reciprocal centimeter. Okay? So these are the key features of alcohol. Now, here is infrared, spectrum of butanediol. So first thing is you don't see any intense peak between 32 and 3500. Okay, but you do see very intense peak slightly below 3000 reciprocal centimeter. This is because of sp3 CH stretching. Okay? I mean, repeat again, this kind of thing, you probably need it frequently later. Okay? sp3 CH, okay, they have a peak slightly below 3000 reciprocal centimeter. And SH stretching, okay, because S first is much heavier than O, so the SH stretching is of substantially lower frequency than the OH stretching. And also SH is substantially less polar than OH, so it's not as intense. So SH stretching actually appear at here, about between 26 and 2700 reciprocal centimeters. It's heavier, less polar, so this lower frequency and weaker. Okay, so this is SH. And the proton NMR of alcohols we already discussed a lot, so I'm not gonna talk too much about about the proton NMR of alcohols. So the OH protons, it's very difficult. It's hard to directly assign the Bayesian chemical shift value. But how we can tell if we add a D2O, shake it, if a proton signal disappear, okay, and that proton is almost certain OH proton, because OH proton can exchange with D in the D2O. Okay, so this is OH proton. But the signature proton in the alcohol is if you do have a proton connect to the alpha carbon, the carbon has OH group, and that proton is strongly deshielded by electron withdrawing oxygen atom. This proton is strongly deshielded. Usually it's above 3 ppm. For regular alcohols, it's like 3 to 4 ppm. But if you have other side have some electron withdrawing group, you can go to 4.5 ppm. But it's strongly deshielded. Okay. So here just one example. The 2-phenyl ethanol. Okay. So these two protons, okay, they are strongly deshielded, okay, so appears at 3.8 ppm. So these two protons, okay, they are strongly deshielded 3.28 ppm. And those blue protons, okay, those two blue protons, this one, okay, these are two blue protons. It appears at 2.8 ppm. Is why it's such a so high chemical shift value? Because of first those two protons also under indirect effect of electron withdrawing OH group, and also it's a benzylic the proton. So that's the also under the influence of phenyl group. That's why it's around 2.8 ppm. So both those peaks, they are triplet because of in this case, the OH proton does not participate in spin-spin splitting. So this OH proton is single proton, okay, and it's singlet. So these two protons only have these two guys as vicinal protons. And these two protons, only two vicinal protons they have is these two. So both are triplet. And then those two, and those five protons, they are just aromatic protons, appear around 7 something ppm. And the protons, alpha protons of thiols are less deshielded because of SH is less deshielded than the OH. And for the mass spectrometry, I want to emphasize, the alcohol is very easy to lose water, in the mass spectrometer. So the molecular R usually is weak. And the one special thing I want to emphasize a bit for the mass spectrometry of alcohol is primary alcohol. So if you have a primary alcohol, if you want to knock out a single electron from this alcohol, which electron is most likely to knock out? So if you want to knock out single electron from a molecule, the most likely way is the electron will be knocked out from the electron that occupies the highest occupies the orbital with the highest energy. So which orbital here is of the highest, which electrons are of highest energy here? We have all the bonding electrons and the two lone pairs. Which electrons are of highest energy? Bonding electrons or non-bonding electrons? Lone pairs are considered non-bonding electrons. You think that the bonding electrons are of higher energy or non-bonding electrons are of higher energy? Non-bonding one, lone pair of high energy or bonding electrons of high energy. Can you hear me? Yeah, of course, lone pairs because only stabilized by a single nucleus. And bonding pairs they are stable at least two nuclei. So the energy always not out from one of lone pairs. Okay? So this will give you a molecular ion. And this molecular ion can easily undergo a fragmentation by breaking off LQ radicals. And this gives you this cationic species fragment is a conjugate acid of formaldehyde. Okay, and this also you can write another form. It's more familiar, like typical carbocation form. But obviously, this form is of greater stability because every atom has octet, and this form has one extra bond. So this guy has a mass charge ratio of 31. So if we have primary alcohol, often when they have a pretty strong MS peak at 31 because of this, the fragmentation process. Why? Because this carbocation is one very stable carbocation. is possibly even more stable than conventional tertiary carbocation because of the, this fork where you have extra bond.